Hello and welcome to Lecture 1 of Introduction to Robotics. I'm Aaron Becker, and in this course we're going to be using this book called Robot Modeling and Control. There is a new version that just came out this year, so you can follow the link there to try out the first chapter. If you like that, you can buy the new version. I'm going to be using the first version, but either version will work well for you. So we're going to talk about what this course is really about, because you need to decide whether you really want to be a part of this course, if it'll teach you what you want to learn. But before we get in there, we need to do some background. And so, what is a robot? Well, this robot actually comes from a Czech word that means work. And so there's a playbill from a play, but this actually came out in a play that was called Rossum's Universal Robots. And it's a delightful little work, like most all science fiction about robots. It doesn't turn out very well for the humans in the end, but it's a delightful look at history, and it's also the first introduction of this word. But in our class, we're going to say that a robot is a tool that is reprogrammable. It's a multifunctional manipulator that's designed to move stuff around. And so this is going to exclude a lot of things which some other people might define as robots, and we're really going to be focusing on industrial manipulators. But the history of robotics, as we define it, is in this last century, where the first robots were derived from a combination of teleoperation and numerically controlled milling machines. So teleoperation was something that needed to be done when you want to work from a distance on something. And most of this was done by the U.S. Atomic Agency, where they were trying to work with things that were very dangerous and wanted to move people away. There's also a lot of opportunities for this in manufacturing, so working with very hot or dangerous materials. And then the other side is numerically controlled milling machines. And so I've got a picture of the toy mill that's inside my lab. I say toy mill, it's really sort of a hobbyist level mill. But it's got some servo motors on there, then it's connected to a computer, and so we can program it how far to move each of the different axes in order to make the tool move where we want to, so that we can remove material from a block of metal. And so the combination of these two, how do you make some manipulators, can manipulate something from a distance under computer control, is the history of where robotics came from. And so it's up to you then whether these things are robots. And so in our class we're going to have an interactive game for this, but you can just decide for yourself, is this a robot? Is BB-8 a robot? Or Wall-E? Or Big Hero 6? I like to think that there are robots. We get a lot of inspiration from those. But in this class, we're going to say that these are Hollywood actors. So on the left, those are not robots. Whereas on the right, our robot is going to be some sort of industrial manipulator. And this right here is an adept robot, but it's got 6 degrees of freedom, and they're made for repetitious, and they're made for factories and for automation, industrial automation. Now, I think that robotics is great, but not everybody should be in robotics. But if you do join robotics, know that this is absolutely a growth industry. And so this is the latest news that I could get, but there is year-over-year projected growth, especially in manufacturing, but now more and more in the service industry. This is just looking at industrial robots, so it does not include things like lawn mowing robots or vacuum cleaning robots, or what we're going to see a big push in is self-driving cars. But it's still a growth industry. To go a little bit closer to home, Houston has identified robotics as one of the top 3 growth areas, which is good for those of you who are local and in Houston. And here are just a few ideas of where the growth will be in robotics. We are a manufacturing hub, but that's going to go everywhere from plastics to medical devices to food production. We're also having a focus area for robotic logistics, as more and more of our products are delivered and sorted and sent to us robotically. And the other one is in robotic exploration. So we are home to NASA, also to the oil and gas industry as the energy capital of the world. And we also have the largest medical center in the world. And so all of these are places where robotics is necessary. You need to know that this course will use a lot of mathematics. This material can only be learned from solving practice problems every day. And so every class will have an in-class activity, and I want you to come prepared to class and to not fall behind. So every day we also have a reading that you should do before class and then watch these videos. So some immediate action items for you. Brush up on your math, especially your trigonometry, and then your linear algebra. If you go into your book in Appendixes A and B, they've got a wonderful review that's going to be useful. Even if you already know that, just read through it quickly. If you don't know it, then you need to study it a bit more. Another thing that I really want to encourage you to do is download Mathematica. It's a software that I use to do a lot of animations for class, and it will really help you do your homeworks faster. Towards the end of the class, we will use MATLAB for some of our assignments and examples. Those of you at University of Houston, you learned that in ECE 1331, but you've got at least a month to brush up on your MATLAB skills. We have a free campus-wide license, so take advantage of that. It's free for now. Once you graduate, it becomes expensive. And so, again, I want to hit this Mathematica. I use it for playing around with robots. There's some links here that I'll put in the description, and you can see some of the things that we've built in this class before. I like it because robots are expensive, so it's nice to be able to animate them and explore some of the concepts. It is a free download for all UH students. And then as a little bit of incentive, if somebody in this class makes a Mathematica demonstration, and I want to do that in collaboration with you because I've got a lot of insight into that, and gets it accepted by Mathematica demonstrations, then I will add between 2.5 to 6% to your final grade. Now these have to be rather polished, and you'll see links. If you follow those links, you'll see them. But students in the past have used that and have made a resource that other people can benefit from. Well, I am Aaron Becker. I started at 2014 here at the University of Houston. Before that, I did a postdoc at Harvard Medical School and Boston Children's Hospital. And before that, I did a year postdoc at Rice University. And I got my degree in robotics at University of Illinois at Urbana-Champaign. You can also follow that link and see my google.com citations, because papers are the way that as an academic we share the results to the world. There's a picture with one of our magnetic manipulators in my lab. This is a picture of my family, and so some of them really like robotics. There's my wife and my 4 boys. I point this out because I live on campus as a faculty in residence. So there's an arrow to where I live. If it were a normal semester, I'd say stop on by, but we'll figure out what to do this semester. This course is about learning fundamental concepts. There's some things that are going to be different because we're going to be doing this course remotely. What I want you to do is to do the problems by hand first, and then use a calculator or software to verify those. For our quizzes and exams, we're going to say no calculators are allowed. You're going to have to use a computer, but we've got a pretty comprehensive honor code for what equipment you can use. And we'll talk about that in detail during the class time. Again, we are having a required textbook, and we are going to go very closely chapters 1, 2, 3, 4, 5, 11, and 12. The other chapters are great, but it's just too much to cover in one semester. For those of you who are coming in person, please bring it with you. If you are remote, then do that. I want to point out that Chapter 1 can be found online at that link from the manufacturer's site. There is a new version, and that's the link to that new version, whereas the old version you can rent from anywhere between $50 to $91. In this class, we do have a final project where I want you to build a robot and do something with a robot that's exciting. And for that, I let you be in 3 to 4 member teams for the final project, whereas for the graduate students, I'm requiring all of you to build a robot arm in 1 to 2 member teams. And so I've got some pictures over here because there's a concept there. On the left, 4 Hulks that are working on a team. That would be an impressive movie, but it's not the kind of team I want. So unfortunately, most of you mechanical engineers, you know mechanical engineers. Computer engineers, you know computer engineers. I don't want you to work just with people who are just like you. I want you to find a diverse team, kind of like the Avengers movie. But the Avengers are a diverse team, and from that diversity comes some strength. Now, so we don't want that on the left, but what I also don't want is something like Endgame, where they're like, well, let's just try. If 5 superheroes are good, let's put 100 of them in there. And so I am limiting you to a group of 3 to 4, or else there's not much contribution that the extra people can give. So we are going to have you guys purchase a robot kit. And again, I'm saying that this semester that's only for the graduate students. I'm going to require you in teams of 2 to purchase a kit like this and figure out how you would do that project. The first lab is just building the robot, whereas as we go in the semester, we're going to add some feedback. So here's an example of that kit. And so you can see that here we've put on a bunch of gears on the sides, and we've also put some potentiometers. So these potentiometers allow us to measure where the positions are. Because a kit, as you get it, is not a robot. There's a human in the loop that's actually just telling the motors when to go on. But by the end of the semester, we'll use an Arduino to control this, and then it will be a full-fledged robot with feedback. I'll give more details as the semester progresses. This is the final, one student's version of it towards the end. And then I will buy little wires for you that you'll need for this. So now let's get started. This class is all about how do we model a robot. And when we have a robot, our robots are going to be what's called a serial kinematic chain, which means that our robot is going to have links that are connected by joints in a chain, one after the other. And there's only going to be 2 different kinds of joints in this class. One is going to be revolute, which is much like your elbow is a revolute joint, and a prismatic. You don't have any prismatic joints in your body, but if you take a pen and slide it through your fingers, this right here represents our prismatic. It has got 1 degree of freedom, and it can slide back and forth. And these 2 drawings that I have here are how we're going to draw these joints, because it's something that we can draw quickly to represent them. The revolute joints are going to be represented by the letter R, and a prismatic joint by the letter P, and then we'll put subscripts so we know which joint we're talking about. And these subscripts tell us which joint we're talking about. And so the ith joint, let's say that this is joint 2, it's going to connect link 1 to link 2. When joint 2 moves, then link 2 is going to move. In this class, we're going to say the axis that a joint rotates around is going to be defined by Zi. So this right here, this joint that I'm rotating around, this is going to be Z2. Then if we have a prismatic joint, we say that the direction that slides, that is going to be the Zi direction. So Zi is oriented along this direction of movement. And so in this class, our joint variables, all these revolute joints, are going to be theta. So theta 1, theta 2, theta 3. And our prismatic joints are going to be represented by d, the depth of that prismatic movement, d1, d2, d3. So right over here, we've got our first robot schematic. What type of robot is this? Define it by using R's, RP's. All right, you are right. This robot is an RRR robot because it's got 3 revolute joints. And we're going to describe the configuration by what is the angle of each of these joints, theta 1, theta 2, theta 3. So an RRR, theta 1, theta 2, theta 3. So now it's time for some vocab words so that we can be talking about the same thing. If I tell you I want the configuration of your robot arm, what I'm asking for is a complete specification of the location of every point on your robot arm. So if we think about my arm right here, if we say this is a robot, there's a degree of freedom. We can move this joint, we can move this joint, and the wrist joint. And so if I told you what angle the shoulder, the elbow, and the wrist is, then you would know where the rest of my arm is. That would be a complete specification of this robot here. And so the configuration space then is a set of all possible configurations. We denote a configuration by a vector Q, which is bold in this class, and then that vector will just be what is the angle of each of these joints, or what is the depth of the prismatic movement for each joint. And it'll be for, if we've got n joints, then it'll be a 1 by n vector. And so here's our example over here. This is a 2 degree of freedom robot on the left. And then if we want to talk about its configuration space, the space where this moves, since each of these joints can move in a circular arc, the configuration space for that is going to look like an interesting and very delightful topology. Configuration space is really the outside of a torus, because we can specify each point on that torus. You can think of that as a glazing on a donut. We can specify each point by its theta 1 angle and theta 2 angle. Now when we talk about degrees of freedom, we want to know how many numbers do I need in order to specify a configuration. And that minimally is a nice word in there. What's the simplest way that I can fully specify where that robot is? So now I want each of you to pull out your cell phone. I'm sure you've got one. This is an object in space, and I want you to think about how many degrees of freedom does this object have. And when we say how many degrees of freedom, we're saying how many numbers do I need in order to uniquely pin this at a certain position and orientation in space. And so you can think about this. If I hold its x position, so it can't move in the x anymore, it can only move in the y and the z. So I can pin all three of those down. And now I've specified the location of one point of this robot, but I can still roll and pitch and yaw about that point. So I need 3 more numbers to fully specify this position and orientation in the world. Our positioning in this class, we're going to have x, y, z for our position, and then roll, pitch, yaw for theta, psi, phi. And for that reason, most manipulators have 6 degrees of freedom, because that's a minimal number you need in order to be able to put the end effector, the end of the robot, in any position and orientation. Now, for a little bit more money, you can get robots that have more than 6 degrees of freedom. In that case, we say it's kinematically redundant, because now it can have multiple solutions to get to certain orientations and positions. You, my friends, are kinematically redundant, and you can prove that because if you take your hand and grab something in the world, you can still move around even though we've pinned your endpoint. And having that redundancy allows us to make trade-offs and allows us to minimize the amount of movement or minimize the amount of power we need in order to do that movement. Some more definitions. So the tricky point is, what is the difference between a state space and the workspace? Well, the configuration is talking about what is the geometry of the robot. It doesn't say anything about how fast it moves, the dynamics. And so if we want to talk about the state of a manipulator, then we're asking for more than just a configuration. I want all the variables. And that's a control systems idea. The state is everything I need to know, so that if I know what your inputs to your robots are going to be for the future, where that robot will go. And so in the state space in our class is going to be what are the positions of all the joint variables. So our angles and our prismatic depths, and then how fast are all those joints moving. So that's the state space. And so if you have a 6-joint robot, its state space is going to be 1 by 12. Now the workspace is the total volume that can be swept out by the end effector of the robot as it moves everywhere for all possible configurations of the robot. Where can that end effector be? And every robot has a different workspace, and we'll talk about that. The reachable workspace is every point that it can get to, whereas the dexterous workspace is every point where it can go, where it can also control all orientations, the end effector. As you can think of your hand, as long as I'm close to my body, I can move it in all sorts of orientations. But if I stretch it way out, I'm limiting the amount of orientations that I can achieve. And if I'm way stretched out, then I actually can only achieve one orientation of that hand. Well, I can also do a roll, but I've limited some of my dexterity. So in this case, I've got 3 joints here on this robot. They are an RRD. And so then I need to have the time derivatives of the theta 1, the theta 2, and the depth. Lots of other ways you can talk about robots. We could talk about their power, or how they're controlled, or whether they're for assembly or non-assembly, or how they're built. And there's a nice link there. ABB has a robot selector tool that you can play with. If we want to talk about how they're powered, on the left, that is a Mitsubishi SCAR robot. Whereas in the middle, we've got a bunch of hydraulic robots that are building cars. And on the right is an all-pneumatic robot. Electrics are nice because they're, in general, cheaper, cleaner, and quieter. And so you can put them in a clean room because the electric motor doesn't have any hydraulic fluid or pneumatics that might release something, contaminants. The hydraulic is definitely stronger. You can put a lot of power through hydraulic, and you can locate your pumps for your hydraulic motors away from your robot. However, you have some problems that you can have some aspiration of that hydraulic fluid, and they tend to be noisier. And then finally, pneumatic, they're often inexpensive. They can be simple, and they can, traditionally the precise control is hard, but there's some amazing advances that are being made in pneumatic motors right now. And so, but those ones, they're not cheap. Right? We can also classify our robots by how do you control them. Is it a servo, meaning that there's a feedback loop, or is it non-servo? And so you're going to see how much fun a robot is during the Robot Lab 2 when you take your robot and you try to control it just by turning motors on for a specific amount of time. And what you'll see is that it's not very accurate. Whereas if we put a sensor on that, then we can close that loop, and we can do much better. And then servo, you can also divide that into point-to-point control, or you can say, I can do a continuous path. And there's more complexity as you do that. And then finally, your robot can be serial, or it can be parallel. And so a serial kinematic chain, you can think of your arm as a serial kinematic chain. If I take both my arms and lock them together, now this is a parallel manipulator. It can be much more rigid, but the math is harder. And so there's some beautiful robots. If you ever get to see an assembly line in work, especially for packaging, these parallel robots are beautiful. They've really taken over. They look kind of like spiders. Now, when we talk about a robot, most people think just of that mechanical arm. But there's so much more to it. That mechanical robot needs a power supply. It needs to have something on the tip. Usually, at least in my case, I buy a robot arm, and then I have to buy the tooling that goes at the end of the robot. Most robots don't even come with a gripper. You have to buy that. There also has to be a computer controller, maybe some external sensors. We've added ultrasound onto our robot arm in our lab. You need to save your programs and control it somewhere. And then usually you need some way to teach the robot. We call that a teach pendant. In our case, for our robot, we use this as a teach pendant to figure out where all our positions are. But there's much more sophisticated ones. Most of the complexity in this class is going to be because we use rotational joints. And there's bad things about rotational joints. They're going to make our math harder. They cause lower resolution. As they rotate, they can cause other effects in other joints because they're not just moving in a single direction. And so you can cause resonance in other joints. You're causing dynamic responses further down your kinematic chain. But the real reason why we use them is shown here. Because if I have a robot where I need to move d distance, if I've got a prismatic joint, it's going to slide through that whole d distance. Whereas if I did a rotational joint, I'd be able to do twice that distance. And so we get a much larger workspace very quickly by doing that. You'll notice that your body has no prismatic joints unless you count the large intestine. And so there is some efficiency in that, which is why you've been designed with rotational joints. Other thing we're going to do in this class is we're going to simplify our lives because we're going to assume that at the end of our robot we have something called a spherical wrist. We'll spend a lot of time talking about this later. There's many reasons why we do this. First off, it makes our math much easier because we're going to be able to decouple. We can solve for the orientation of the end effector separately from solving where the rest of the joints of the robot should be. So it takes our problem from being a 6x6 matrix to being just a 3x3 matrix and another 3x3 that has a plug-and-chug solution. Now in this robot, a spherical wrist, you'll know it if you have 3 rotational axes that all meet at a single point. The single point is called the wrist center point, and you can do that. Lift up your arm right now. If you roll your roll your forearm, and then you can bend your wrist, and then you can spin something with your fingers. It's much more impressive. I put a screwdriver in my hand, right? And so I can roll my wrist centers right here. I can roll that. I can bend my wrist, and then I can spin this as well. And it makes our math much easier. You got to buy a robot hand for your robot. If you go up to my lab, you'll see that the robot hand that I've picked for our UR robot is just going to be a parallel jaw gripper. You say, well, your hand isn't a parallel jaw gripper. Why would you buy that? It was to save money, but that robot arm, the hand that I have, is still about $3,000 to $5,000. Whereas this 3-finger robot end effector, shown down here on the right, costs several times that. And so the big reason is we can simplify a lot of our math if we have a parallel jaw gripper, and we can design the test so that the parallel jaw gripper can accomplish everything we want. The principle of parsimony. We want the simplest solution that works. In class, we'll act out the different robots. This is our articulated manipulator and its workspace, the spherical manipulator and its workspace, the scar robot, the cylindrical robot, and finally the Cartesian robot. And so they all have different workspaces. You pick your robot type based on the kind of applications you want to work with. So a spherical robot is very good if you are doing a camera that needs to be pointed anywhere, or a gun turret. A scar robot was designed for pick-and-place operations for building circuit boards and assembly. The cylindrical robot is very good for fetching objects from a warehouse shelves. A Cartesian robot is ideal for CNC machining. So the cool thing about this class is that everything works together pretty well. What we want to do is learn some fundamental concepts. But here's a 2-joint robot. We want it to go from its home position to some point A and then trace out some contour to B while applying a force. And then we're going to use some feedback from a camera so we know whether we're doing it correctly. So what I want you to do is work through the Chapter 1 textbook examples. We're going to have a quiz on Appendix B on Wednesday. And I'm going to ask you to have submitted your pictures by Wednesday so I get to know who my class is. I really want you to read Chapters 2.1 and 2.2 from Appendix B for Lecture 2 so you can come prepared for each class. It's good for you. Advanced reading will help you understand it with much less effort on yours and my part. There will be a quiz on Wednesday that's based on your assigned reading. And now it's time for in-class worksheet. All right, so we'll work on this in class when you come. I'm really looking forward to this semester with you. Please give me feedback. A good way to do that is by emailing me or leaving a comment below.